as usual, I'll just review a tiny bit. We got the ginormous kinetic energy and radial plus a Coulomb, right? This is the H atom. The potential is incredibly easy. It's just, 1 over r. It really could not be easier. Of all the things that you can tack into the Schrodinger equation is always easy until there's a potential energy. But that potential energy is 1 over r, and that's radial. That means we have to turn the kinetic energy into radial, and then it all heck breaks loose, right? So the angle parts, for reasons I don't really fully understand, I even tried to look it up, are separable. And so basically the way that the theta and phi parts filter down is as it's like contributing the rotational part of the energy. That's one way to think of this, is that, again, the theta and phi's basically just toss this into the energy. It's just a bunch of constants, right? You can just kind of bring it over here, except for the r squared. But anyway, all right, so there you go. Now what you do with this thing is, now that you have it, I'm not quite sure, I don't think that the solution to this thing was some 18th century math textbook deal. I'm not quite sure where the solution came from. I have to look that up. It's kind of fascinating to know that a lot of this was solved in like 1783. But anyway, as I've said a zillion times, what we do when we have the Schrodinger equation set up and we separated and understood all that we could, energy increasing, energy decreasing. I then give you wave functions and we start tinkering with them. So let me do that. What I want to do, though, is I mentioned towards the end last time, I mentioned how you have two different types of potential energy surfaces. You've got a L equals 0. I drew that. I didn't draw that right. Let me get that right. I want to point out that actually the potential is at best 0. Notice that the potential energy, this is purely negative. So for an L equals 0, the energy is always below 0. And then for higher angular momentum, what happens is the Coulomb is in charge until you get real close, and then the angular, and then this part's in charge, and that's energy raising, right? So for an S state, the energy just keeps dropping, just because of Coulomb's law. So that's obvious, right? It's just, notice I just drew 1 over r potential. Now this is positive and it's 1 over r squared, so at close distances it starts to dominate. Now remember, and this is sensible, every now and then this is actually sensible, right? That's because a p or d state, as the electron gets close to the nucleus, turns faster. And it happens to overwhelm the Coulomb. The positive spin outweighs the negative Coulombic attraction. So anyway, so this is for L greater than 0. P and D, that's what I mean, P and D, just call it P and D. All right, anyway, so the solution introduces a quantum number, which we know actually corresponds to the row of the periodic table. That's kind of cool, I think. SPD, PX, PY, PC. All right, so real simple. Okay, now it turns out that the radial wave function has energy filtered down to it as these separable deals always work. When we separate a wave function, especially when we have 3 variables, one of them doesn't do much, then the next one gave us the rotational energy. The last one gives us the real energy. It always filters down that way. It's a little game of pinball. And so I get wave functions, I get energies. I want to point out that, sorry, I'm looking for the wrong set of notes, that would help. What I'm going to do is, here, let me show you what the big picture is. As we talk about radial wave functions, it turns out that they tend to look like this. I'm going to write them all out. I'm going to write down, for SPD, for 1, 2, 3 shells. I'm going to write down just a bunch of wave functions. But I just want to point out to you, they always look like this. There's an r to the L, which is like responsible for the wave function's behavior, which means the electron's behavior at close distances. There's a little mathematical connector, and e to the minus CR, and an exponential decay. Right, so again, this part takes care of how it spins around the nucleus, and that's close and far away. There's just this exponential decay, and then of course there's something that bridges the gap in between. It's like makes it smooth and continuous. You kind of think of it that way. This guy is actually kind of important, so I'm going to put this on a homework. I don't have time to cover it. When you'll see on your homework, you can kind of whittle this equation down for long distances. If you say r is very big, you can basically eliminate some of these terms, and you find that a solution of the type e to the minus r is valid. That guy is actually real important. It says that wave functions drop off exponentially. It's kind of hopefully intuitive at this point that that would happen. But what it means is that quantum type of phenomenon occur, they occur, right? And I'm thinking specifically, some of you, now what do you think about your jobs? Oil industry, what about materials, right there? What about materials industry? And you think of material, what about electronics?
Yeah.
Lots of chemicals, and I think you're chemical engineers, overwhelmingly chemical engineers. Electronics companies use tons of chemicals. Trust me, that is a big market and lots of money. So probably kind of more interesting in oil, right? So think about that. Now, it turns out that if you work in a materials company and materials are probably going to be going into making semiconductors, semiconductor design has a lot to do with, okay, well, the electrons are going between source and gain with a gate, and you've probably heard all these terms before, but you'll always hear that, oh, well, this phenomenon dies off exponentially. That's this. Whenever you're talking about electronics, especially high technology electronics, CPUs and whatnot, and transistors, really nanometer scale transistors, that's what everyone wants, right? You'll hear about the design criterion having components, phenomenon that die off exponentially, and that is actually what's doing that. Quantum phenomena dies off exponentially. So, so anyway, I'll have to have that part on the homework. As for this guy, I'll do this one in class. And the way to do this at close distances, you can read that, at close distances, what I'm going to do is, just so you know, so you can follow along algebraically, I'm going to multiply 2 times the minus 2 times the mass over h bar squared times r. So I'm taking that thing on top, I'm going to multiply by that, and then I'm going to eliminate the r terms at long distances and keep the ones at short distances. And the point of that is that then I will show that that's valid. That's what I'm trying to do. And again, I want to point that out because this guy dictates, this is the thing that keeps electrons from smashing into nuclei, which keeps the universe from blowing up. And I think I mentioned to you that whenever people were solving these, back in the 30s, when they're solving all of this big fundamental stuff, every now and then, like on your homework with the Bohr model of the atom, they'd make great progress, get lots of good answers, but something would fail, and they'd start over. And that was the right way to do it. So heads up on that. Okay, so I have to follow my own notes, which is a little, okay, minus, I have a minus sign. Actually, I think I just multiplied, not by minus, I think I just multiplied, yeah, sorry, by plus. Sorry, I just got rid of the constants, I kept the minus sign, and you've seen how that can bite you. Okay, r, sine of r. Okay, a lot of those constants go away, that's kind of nice. And just over r squared. Okay, so
You
one.
can say squared there. With the first term for the derivative.
Say again? Oh, that bit?
Yeah.
Yeah, thanks. All right. So, let's see, then I've got minus e squared over 4 pi e naught r psi of r. Notice that one reason that I'm doing it this way is because when we were whittling down and playing around with these operators, which you've seen a zillion times, you can make these operators look like a bunch of different ways, and you've seen a zillion examples of that. It's nice that the radial part is so simple, but you end up with r times the wave function. So what we like to do to make the solution easy for the mathematicians is multiply everything by r, and that's so that so what they're not actually solving for the wave function, they're actually solving for r times the wave function. And again, if you are interested in the pure mathematical derivation of the answer, then that's actually kind of important. Okay, so there's that. All right, now at low r, let's see. Now I'm going to get rid of some things. Okay, I'm not going to get rid of that because that's kinetic energy. Getting rid of that, that's always going to be a bad mistake. Remember the Schrödinger equation, the bad is always the kinetic energy. He always, it's terribly important. It's the double derivative. That's the part that always makes this a heck of a pain in the rear. This guy is important at low values of r, and that's because it's got 1 over r squared. This guy, the r dependence is actually gone. For one, this is proportional 1 over r squared, this is proportional 1 over r. Notice that I multiplied it all by r. So this guy just doesn't carry the same weight, so we get rid of it. Same thing's happening here. R, again, is very small. So this has no r proportionality. This is proportional r, which is worse, because again, r is small. So what I do is I wipe that out. And that, of course, means I make it 0. Now what I'm then left with is these things here, and plug in psi is r to the L with some normalization. Who cares? Again, that homework hopefully got you a little bit more comfortable with normalizations or not normalizations. Okay, so now what I do is to show that this works, and then I'm just going to write down a bunch of wave functions. So I've got r times r to the L, and that better equal minus L times L plus 1. I just set that term to the right over r squared. No, just r to the L. I just did a little factoring there. Okay, so this is r to the L plus 1, so I bring down an L plus 1. I'm left with the derivative of r to the L. I can do some factoring a little bit more on this. This is r to the L minus 1, right? Again, that's just algebra. Then this is ends up being L times L plus 1. Did I make, what did I, I'm missing a minus sign right here. Sorry, minus sign right there, right? I multiplied by times mass of h squared, not minus. Sorry.
They're fixing the water pump.
The water pump.
Huh?
They're fixing the water pump.
It's shockingly loud.
It's called water.
Okay, well, let's just try to live with that. Sorry, folks. I'll call them to fix that anyway. Okay, so the way to put that, Jesus, that is so annoying. Anyway.
I know.
Class outside.
Well, I don't have a choice. We have to live with it. We're kind of behind schedule right now. Anyway, all right, so the point of this is it works. Okay, so R to the L is indeed a good answer for when we shave down the Hamiltonian. So let me again summarize this in a big way. At close distances, I shave down the Hamiltonian, cool, then propose a solution, R to the L, and it seems to work out just fine. That's what you just saw. Now, for your homework, so at close R, the wave function is R to the L. At far distances, the wave function is just an exponential decay. And I'll have you, what I just did at short r, I'll have you do that on a homework for far r, for long distances. And again, you basically just, you pick different terms and cancel them out. Obviously not the ones that I canceled out for this one. And you'll find that this works. And there you go. Again, part of this is just to understand the nature of the solutions. Because these two things are always there no matter what. And with that said, let me start writing down the actual solutions. So again, remember these are approximations. Now, another thing that sets me off I don't mean to sound angry. Poor Marina had to get an earful when she made a slight thing, and I just was like, why don't you do that? Oh, God, oh, God. So I'm sorry. I tend to be like that, especially if you do those operators wrong, like I was talking about at the beginning. Don't let me scare you off, all right? But, so the thing that gets me, that just will make me blow up, is when you get confused about what these wave functions really represent, right? So recall that n is our quantum number that keeps track of solutions for the radial equation, okay? And it also happens to correspond to the row in the periodic table. Okay, now I only got an n of 1 solution because I made L equal 0. There's no n equals 1 solution, L equals 1 solution. And let me put that in more familiar language. There's no P, there's no 1P state. There is a 1S state. There is no 1P state. That does not exist. There's no 1D state. The periodic table is not arranged that way. Okay, so there you go. And the wave function, now don't forget there's an angular wave function too, and I'm not writing those down. This A naught is just due to a bunch of constants because there's like, you know, a bunch of H bars and a bunch of masses and, okay, so there you go. This is the ground state. Now the thing I was going to tell you that makes me just go bonkers is some people say that this is what hydrogen is and nothing else. So that there's no such thing as a 2s state, that like they don't exist. No, that doesn't make any sense at all. This is simply an excited state. So hydrogen with the proton and electron in the ground state has this wave function. I can take hydrogen, I take H2 gas, I have to put it in a chamber, I have to kind of do something funky like put a bolt of lightning through it, break it up, and I've got a bunch of H atoms in their ground state. I can put them in an excited state. And I have all kinds of ways to do that. I could heat it up, I have to get really hot. I could shoot UV light into it. There are many ways to make hydrogen, get that electron to an excited state, and that's all it is. It's still a hydrogen atom. I never quite got why, that again was a common mistake. Again, a bunch of constants that I don't really care about. But what you may notice here, if your math is savvy enough, you don't have to be that savvy, you may notice that when I write polynomials, I'm introducing nodes. Right? If I have just, if I don't have anything, this is just an exponential decay, there's no room for a node. But as soon as I start putting polynomials in front of the exponential decay, notice that the exponential decay changes a little bit. Not a big deal, just, I don't want you to think it's a typo or anything. So that little spacer here creates nodes. We've seen that kind of behavior before. You saw that in vibrational wave functions. There's a little spacer. There's a little term in front of the exponential part that introduced nodes. You're seeing that again. Okay, now question though. Now I said to you there's an R to the L component, every one of them. So where the hell are they? I said that these things exponentially die off. You see that? Where's the R to the L? I said there's an R to L in every one of these, but I don't see it.
That was the 1 over n.
And the L is equal to what?
0.
R to the L is
1.
right. It's there. It's just hiding. Okay, so now let's do 2p. Now you see it. So I'm pulling your leg there. Maybe that's an early question on the next test. Okay, a bunch of constants that I don't really care about. Again, I showed that you have to be careful of that depending on what you calculated. Okay, here's kind of a cool thing. I still end up with a node. It looks a little different. And here's my exponential decay. And again, the A naughts, and those from your homework, you hopefully know that those are Bohr radii. Basically, they just mop up all the constants. From, you know, H bar, mass 2, 4 pi E naught, permittivity of space. They all can get sucked up into the A naught constant. Fine, right? That's nice. It happens to have, it comes out to have units of length. It's about 0.05 angstrom, something, 0.5 angstroms. I'll write it down in a second. But anyway, okay, where's R to the L?
R to the 1, right?
Yeah, there we go, R to the L. So it is there. So don't get confused. Okay, that's a P. Now let's do a 3S, and then I'll draw some of them. Okay, N is 3. This is an S state, so L is 0. And as I mentioned before as well, these things get big really quick. You know, again, some brilliant mathematician back in 1800 or whatever it was solved these things. There's little algorithms, by the way, recursion formulas that that can give you what these things are. It's not like they had to figure out every state by hand. Again, if you're super mathematical, you can solve these. Differential equations, and again, if you're very good at this, you don't just solve them. What you solve is a recursion formula that gives you any nth state. And remember, n is the quantum number. And notice that the exponentials kind of get weaker and weaker. Notice that we start out with r over 2, and now we've got r over minus r over 6. Does that make the wave functions bigger or smaller?
Bigger? Because
Bigger.
it's negative, right?
Well, bigger, because, so think of dividing. See, I'm trying to trick you. It's a bigger number, so you think it's probably smaller. It's actually bigger, right? Because r has to get bigger to dilute it. Think of it that way. For this to have the same value, r has to get correspondingly bigger to basically get rid of the higher number here. So the wave functions spread out. This is my point. The higher the excited state, the electrons get wider, and they get further away from the nucleus.
I have a question. So for the 2p, you don't have that spacing difference that you said, so does it mean that...
Say again.
So for that stage, yeah, you don't have the spacing difference that you said, so that means that we don't have a node?
This does not have a node, right? This does not have a node. That's correct.
Okay.
Yeah, and I'll draw those, and it's more, I have to think about it for a second. I don't like to try to look at these, the information's here, obviously, and if I had a graphing calculator, I'd figure that out real quick, but there's a little mnemonic, there's ways to remember that from the graphs. I'm going to draw the graphs here in a second, but no, there's no node,
Okay.
no node here. And you know, the reason that is because that's actually the first of its kind. So remember that in every problem we've ever had, particle in a box, I mean, what are the important ones? Particle in a box, and then vibrational ones, those are kind of easier to put in your head, right? The ground state never has a node. The first excited state has a node. The second excited state has 2 nodes. Okay, so the first of its kind never has a node. First of its kind, first S state, no node. Then I pick up a node, it's the second of its kind, but that's the first of its kind, it's the first P state. And so no node, there's no node here, I'll graph that. So a 3D state, no node in the radial. Again, first of its kind. It's picking up energy from its angular momentum, that's why it's an excited state. And last bit I want to point out is that these get wider. So on your homework, I have you do what I do with every one of these problems. I give you some wave functions and I say, okay, tell me this about it, tell me that about it. And what I have you do is I have you calculate average distance on the present homework. And that's going to lead to some integrals, and look at the integral identities. It's the only thing hard about it is keeping track of all those freaking constants. Sorry, let me finish this part up here. Where A naught. Now I remember why I got it. So it's again just mops up all the constants. Don't worry about it being on that. It's 0.052 nanometers, and that's basically half an angstrom, right? We like to express, angstroms are not SI, it's an angstrom is a tenth of nanometer, a nanometer is a standard SI unit. A little funky there, but the reason we like angstroms, that bonds are typically 1 angstrom. Carbon-hydrogen bonds, hydrogen-hydrogen, it's all about an angstrom. When you get to inorganics, they can be about 2 to 2.5 angstroms. So angstroms are for the unit, but they're not standard SI anyway. And again, you saw something like that in your homework. All right, now what? Okay, let me do the energy, and then I'll graph these things. I'll tell you a little bit about some neat little factoids. So again, differential equation, you get two things out of them, you get wave functions and you get the energy. And now this guy, of course, is a giant mess of units. Mass of the electron, remember that's a little bit not quite right because of that center of mass deal, but don't worry about it. It's such a little factoid, I don't ever worry about it. Permeativity of free space, which is, I know, that thing that makes Coulomb's law work. And this guy, this is the important one, 1 over n squared. Okay, so, a couple things about this. Energy is always negative. Now that's a little weird. I want to point out that this behavior is different than any other you've ever seen. In particle in a box and vibration, rotation, energies were always positive. That's because most of those guys were pure kinetic energy. And in the case of vibration, where you actually had more potential energy, you assume that the lowest possible energy was 0. So you can only go up, right? Energy can only go up. This guy is kind of funky. The energies are negative. Now the reason that is, it's kind of weird. It's because of potential, because you only got one thing in your potential energy, and that's why I caught myself before. A Coulomb potential minus 1 over r can never be positive. So what this ends up looking like is the end states are kind of like in here. And of course they get infinitely close together and they can never reach. Oops, what's wrong with me? So if I was to plot the energies along a potential scale, it looks like this. And dot, dot, dot. But of course, n of infinity is 0 energy. So what's weird about the hydrogen atom, I know it's not that big a deal, I'm just saying, its energies are negative because its reference point is technically an electron and a proton infinitely far away, and those have no energy at all. They're infinitely far away, they're not moving, that's like your reference state, so that's why the energies are negative. It also means that if I want to experimentally, it's more like one of the first P-Chem things anyone ever did was to take a hydrogen atom and tear it apart. How much energy did it take to tear apart a hydrogen atom? Now that of course means to take the nucleus, the proton, because all that's there, and the electron, and pull them all the way apart. How much energy did that take? So it turns out that this is basically, again, work all the units and whatnot. This is minus 13.6 eV over n squared. Again, all the units. Now I'm using a bit of, you've seen electron volts. You had to do a little bit with that before. It's a convenient unit when we're talking about atomic stuff. An EV. EV, is that a big number or a small number? What do you think?
Small number.
It's actually what? Is that well? That's actually a good point. It's actually it's like 10 to the minus 19 joules. One of these is like 1.6 10 to the minus 19 joules. So it's kind of a small number. Now the reason that is because I'm talking about a single hydrogen atom. Now the thing is that in 342 we always did things per mole, right? Because it doesn't. We're talking about car engines. You're not going to talk about a single gas molecule burning in a car engine. You're talking about a mole of gas burning in a car engine. So now, take that to the minus 19, multiply to the 24. What do you get? Yeah, it's a big number. It's actually really per molar, which is kind of what matters to a person as we're like designing engines and stuff. For a molecule, it's certainly, I mean, it is a small number, but for a molecule, it's actually big. And for a mole, it's a gigantic number. So EVs are actually really quite big. I like to think of them as quite big numbers. If I translated that to wavelength, so what wavelength of light? 91 nanometers. Okay, that is like ultra UV. Okay, where does the visible spectrum kick out? Here's a hint. 520 nanometers is green. 600 is red. So where do we get ultraviolet? Because that's where you stop, your eyes stop working.
Somewhere Somewhere between 7 and 8.
No. 800 is red. Remember, it goes backward.
Oh, sorry.
Right. Long wavelength is actually low energy. It's not, it's a big number, but it's actually low energy. 600 is red. 500 is blue-green. So where does the blue kick out?
204 or something.
It's around. If 400 is blue, and right below 400 is when you're in ultraviolet and you stop seeing it. Now you know that if you're outside and you're getting 390, 380 nanometers, you are burning to death. That's bad. I mean, that's cancer bad. 91? If you got exposed to 91 nanometer light, you're getting cancer immediately. All right, just heads up on that. So that's a fairly large. That's another reason why I'm saying it's a fairly large amount of energy. And I also want to point out, last bit here, and then I'll draw. Oh, here I have it. I'm sorry. I actually have this. I have this here. 1.3 megajoules per mole. Yeah, it's actually gigantic. It's a gigantic number. Hydrogen is the only thing that does this. As you get to heavier atoms, the amount of energy it takes to excite them becomes less and less. Anyway, just a little factoid. One other factoid is, if you look at the absorption or emission spectrum, remember that I actually brought this up last time? The energy was a constant. You recall this? It was 3 lectures ago that there was this little formula that people figured out where N1 was N2 plus 1. You remember I told you that at the very beginning? Right? There you go. Right, it's all right here, N squared. Now, when it comes to disassociation, what you do is you say N2, no, what is it? N1. N1 is infinity. Okay, now the reason that is, and you're going to do this on your homework, is on your homework what you find is that those wave functions, and here I'll write this down for you, when you're calculating the average electron-proton distance, you know how to do this, right? Now, one thing, heads up, I'm going to be mixing Maxwell-Boltzmann and quantum. I'm going to be mixing it more and more because I can. And it also reminds you how to do this stuff. A probability density for a Maxwell-Boltzmann, when we're doing quantum, is the wave function squared. Remember that? Probability density is the wave function squared. Now, what's cool is you don't have any i's, no square roots of -1, so this is a little easier, right? Just square the damn thing. Okay. Now, don't forget this. Multiply by the thing you want the average value of, right? That's two months ago. Okay, and we would go, there's no minus, this is a vector, so there's no negatives. The furthest these can be away. And then I'm going to do this. Is this right? No, why not?
4 pi.
Because I'm there we go. 4 pi r squared, the Jacobian. Don't forget the Jacobian. No, not 4. No, just r squared. Just r squared. Or wait a minute.
Jacobian, move on.
You know what? Where's the 4 pi from in the Jacobian?
From the bottom.
With the 3D.
3D from the angles. It's from the angles, right? Right. The 4 pi is from the angles and r squared. So it's actually, it actually would be eaten up by the normalization. I think it's just r squared. And the 4 pi, we would deal with the angles separately. But anyway. So right, don't forget this. This is dr plus Jacobian. Now, what's happening here is, in case you forgot, is you are integrating, if you take a wave function and multiply by r and integrate, you're working in one dimension. I know you're kind of maybe tired of hearing me say this, but dimensionality is kind of important. And sometimes, as much as sometimes you may think like, oh God, how can I ever keep track of what's what with all these constants and whatnot? This is simple. if you integrate with R, you're doing a one-dimensional integral to describe something that's three-dimensional. That will never work. That's impossible for the result to be correct. So the answer is, of course, is that there's a Jacobian. There's a Jacobian going from 3D to 1D. And that Jacobian ends up bringing in an R squared. Look at that, now I've got an R cubed. Plus, there may be some more R's inside of here. And that's its own business. But notice how, if I'm trying to describe something that's three-dimensional, the Jacobian makes it three-dimensional. So, cool. Okay, now what you find is...
I still don't understand what happened to the 4 pi.
it comes from here. Let's do...
There's a normalization constant?
No. No, because there's actually two other things going on here, right? Right? This is three-dimensional. I'm trying to integrate something in 3 dimensions. X, Y, Z. I've changed X, Y, Z to R theta phi. So if I'm ever going to integrate in space, and I need to do it with X, Y, and Z, but unfortunately the damn SOB is in R theta phi, then I actually have to do it this way. Right? So I am integrating the wave function, the radial wave function here, and what I'm doing here is I'm integrating the angular wave function here. And again, remember this? Remember that? That's part of the Jacobian? You did see that a while ago. And here, let me, this guy is pi. And then you've got this. Then you have the phi deal. And that one doesn't happen to have any constants or sines or cosines. That's just what it comes out. Huh? Okay, remember this? And if you're talking about an S state, this all turns into, so where's the 4 pi? If these are S states, which don't do anything radially, this turns into a 4 pi. Right? It's here, you know, if these are just, if they're ones, if there's no angular deal because it's an S state, integrating sine from 0 to pi and this from 0 to 2 pi this is 2. This is actually like minus 2 pi and that's minus 2, so you look for 4 pi.
What happens if it's a p state or a z?
Well, then you plug in those wave functions and you get what you get. So I'm actually having you do S states for a reason. Easier, right? Well, actually, no, the p states, you can still do the p states because if I'm asking average R, all of that's done here. These will actually be normalized. Technically, they'd actually just get worked out. You don't really need to do it, right? No, you don't. You wouldn't need to, right? Because if I'm asking average R, only the parts of the wave function with an R in them can ever matter. These guys will actually take care of themselves. It actually would normalize itself to non-existence, right? They normalize to 1. Right, so technically what I've not done here is I didn't add the normalization constants, which would introduce a 1 over 4 pi. So it actually gets worked out. So anyway, just look out for that because, again, when you know what though, on the homework or exams, these Jacobians here and here, I will give them to you because you're going to forget, and I forget a lot. So I will give you these Jacobians to make sure you don't screw this up, because otherwise you're just going to forget, and that's like pointless. So anyway, I just wanted to remind you of that. Okay, anyway, now here's what I was trying to get to. On your homework, when you go to higher and higher R's, I'm going to have you do an S state and a 2S state, I think, and you find that the average R increases. And I can tell you that that just keeps happening. So if you want to dissociate a hydrogen atom, what you do is you assume that the electron and the proton are infinitely far away, which means that the final state is technically like the n equals infinity state. At the n equals infinity state, the super highest excited state possible, has the proton and the electron infinitely far away. Right? So I call that dissociated. So anyway, that's where you get the, that's how you calculate the energy. That's actually how they knew. That's how they knew that quantum mechanics was actually right. This was like one of the final tests that they gave QMet was they had, all right, electricity's invented, they have vacuum chambers, they have hydrogen, which you also isolate with electricity. They were able to make hydrogen atoms, they were able to measure how much energy it took to dissociate them. And then they started trying to compare theories that would get that energy right. And quantum, what we just did right now, that's the one that passed. So at that point, they were absolutely confident that quantum mechanics was correct. Okay, next bit, and I have just a little bit of time, and expect this on the exam, expect this on third, maybe final exam. I personally like graphs way better than those. I mean, I know that the formulas, I just erased them. Yeah, I just erased them. I know that I can graph them, so let's graph them. It's way better to look at. I think I'm going to plot 1, 2s and the s states. Okay. And then I'm going to do the p states. I'll probably do that next time. Okay, they look like this. Now, recall, God, I wish I hadn't erased this. Why did I do that? Got to plan ahead. The S state with an R to the L, let me write that down. So the wave functions, the radial wave functions are proportional to R to the L, which for L equals 0 doesn't do much, right? And C is like 1 over a 4, anyway. So for the 1s state, it's just an exponential of k. Right, very easy. Now remember that it actually has, that's important to keep that correct, it actually is finite. It has a finite value at r equals 0, and that's okay for a reason I'm about to express, but here, let me draw 1 or 2 more, and I'm going to tell you a little bit more about why it's not 0 at r equals 0. Okay, the next one, let's do a 2s. Normalization means that it's less intense because it's longer, and so it has more r to integrate to a higher value, so that's properly normalized. Okay, and you see a single node. Now you see the exponential decay, it's from underneath, but whatever. You know that wave functions are meaningless, wave function squareds are meaningful. So the fact that the wave function approaches 0 from below that still counts as an exponential decay. There's one node. Okay, then, gonna have to draw this right. So then the 3s state does this. Try to not screw this up. And it approaches. Now again, you see that it goes out a little bit further. Goes a little bit further, so this is 2s, and this is the 3s state, and there you go. Okay, last bit. So again, I'm just graphing what I just drew. The important things are that there's an intercept, that it's not 0 at r equals 0, and again, count the nodes, but you should know that at this point, right? More nodes means more energy. Before I let you go, I want to point out something. This is kind of important. The fact that the wave function is not 0 at 0, be careful with what I just said, not 0 at 0, I would normally say that sounds bad. That means that the electron could fall into the nucleus. If the electron falls into the nucleus, I've got a Coulomb potential that's minus 1 over 0. That's minus infinity. Negative energy is energy released. So the universe just exploded. So it seems to me the fact that the wave function has some probability of touching the nucleus ended the universe. So something seems a bit wrong with that. The solution is what we were just talking about. That's why I was kind of glad to go over that. What you don't really necessarily want to plot things this way. It's a little misrepresentative because you're plotting something in 3 dimensions in 2 dimensions, right? 2 dimensions because this board is 2-dimensional. Maybe it's 1-dimensional because there's only one r-axis. I don't know, it's semantic at that point. But anyway, this is inherently 3-dimensional. So what you really want to plot is called a radial distribution function. This gets it across a little bit more realistically what's happening. And what it is 4 pi r squared wave function. Right? Where's 4 pi r squared? What is that? Huh?
Oh, the,
Jacobian?
Jacobian. It's the Jacobian, right? Remember, what this is doing is it's actually taking into account the volume element. Okay, so let's take the 1s state and multiply it by r squared, essentially. You can see that I think there's some controversy over 4 pi or not 4 pi. So now this is the 1s state. Still no nodes. You would still see nodes. But what it shows you, and I remember I said this last time, the reason that the universe has not exploded in hellfire is because the wave function, the radial distribution of the wave function is actually 0. Now what this means is that the electron will never plop down into the nucleus because the nucleus exists at an infinitely small point, right? So you see that this is a volume, this basically takes care of the volume. You have modeled the nucleus as as a point. A point has how much volume?
0.
Right, yeah, none, 0. You learned that in geometry class. Because the volume of the nucleus is 0, the electron can never actually hit it, it can never find it. Besides, it also has no volume as well. And that gets reflected in the fact that the radial distribution function does fall to 0 at 0, again, because the electron never can actually hit the nucleus because the nucleus is infinitely small and it can simply never find it. It's actually fair to put it that way. Okay, anyway, folks, graphs of wave functions are absolutely going to be on the test. I put that on there every time. Next time we'll do the 2p states, we'll do the angular bits. Homework set, well, be placed late tonight.